Here's a side view of a spool of thread perhaps, and there's a string wrapped around this inner part. And then if you place the spool, on a table, um, well, by pulling on the thread, you can, well, the spool will roll, and how it behaves can be interesting. It's worth looking around to see if you can find, so spools of thread are great. Spools of spool, especially when there's kind of, if you have a spool of thread where like the outer rim of the spool is like that, and the outer rim of where the thread is like that. Okay, but if you can find a spool that looks more like this, where the differences in those two radii are non-negligible, some neat things can happen. So what we're going to look at is what what we want to really ask is if we know where we're going to apply a force, and we're going to limit our forces to be either perhaps like this or like this. We're going to get rid of angle stuff, right? We're not going to pull up like that, but well, I guess until we do. What we want to figure out is what happens at point of contact. All right, the phenomena at point of contact. There's probably friction. In most quote unquote most cases, there's a frictional interaction that happens at point of contact, and the word I'm looking for, predicting its nature can be counterintuitive and, well, probably not worth your time. Looking at an analytical solution of what happens at the point of contact is of interest to people like you. So, all right. So, all right, it's possible for sure to get a spool to roll in the quote same direction you're pulling. Like, excuse me. For example, if one were to apply a force like that, yeah, this spool does roll that way. What will happen is you will end up with an ACM, a center of mass acceleration relative to the ground to the right. And well, the real reason why, maybe we'll get there in a minute. Well, here's what also happens that can be a little counterintuitive. It people. Come on, okay. If you have, whoops, if you have, why am I bothering? A spool like this, get rid of it, and you pull down here, it might feel like, well, shouldn't this thing like unroll and go that way? Well, this thing also ends up center of mass accelerating. Come here. Boop, boop. You will also get a center of mass acceleration to the right. And there's well, we can justify that without too much trouble if we consider, well, what angular acceleration will these forces create? Well, then you have to say, well, about what axis? All right. And well, if you choose a center of mass axis, there's an R vector like this. And okay, well, wouldn't this force make a that? And so shouldn't this thing, quote unquote, roll that way, an ACM to the left? This one makes more sense, perhaps, right? If you have an R like that, if we choose center of mass as origin, okay, we get a torque like this and an alpha like that. Okay, sure, shouldn't that thing therefore ACM to the right? It does happen to ACM to the right, but so choosing a center of mass axis is not a great place to go because, again, what we're not considering is what is happening at point of contact. There is an interaction, a surface interaction there between spool and whatever it's rolling on, and thus, well, there's a normal force, and that could, and in many cases does, account for a frictional force. We don't know the nature of that frictional force, so running a net torque analysis around some place that's, where we can't include the unknown action of the friction force is not a valid analysis. So let's instead run a net torque analysis from here. Here is an R vector around starting at our chosen origin. Again, where there might be a friction force, we don't know its nature, so therefore, yeah, why not choose that location as an origin? We get to discount any torque created by friction because there ain't none. about that axis. And sure, whoops, that's not the correct R. Here's the correct R. R to our force F looks like this, and for sure, yes, that force creates a torque that way, creates an alpha that way, creates well, an ACM to the right. It does. Okay, well, look, this thing does the same thing. There's an R to this force. This creates an alpha like that about that point of contact, and yes, so therefore this whole thing accelerates angularly that way about this axis, and therefore, well, if what we haven't stipulated yet is these things, let's say they are rolling without slipping. That's a big deal, rolling without slipping. It means that this location point of contact does not move relative to surface, right? And so if we get an alpha, a clockwise alpha, what that translates to is an ACM to the right. All right, you should try this one. Look around, see what you can find. If you can find like a bigger loop of string, try it. This one can be pretty counterintuitive, but fun to do. And you have to just pull carefully again, such that you make this thing roll without slipping. That's the big deal. You got to make this thing roll without slipping. Okay. There are ways to pull where it seems like the thing pulls in the opposite direction of pull, and that would be something. Now, I said a minute ago we weren't probably going to talk about angle stuff, but this one we have to. And now I just want you to notice where I'm saying this string is. I'm saying the string is sort of coming off there, and notice that that string has to pull tangent to circle, right? It's not like we couldn't choose to pull in that direction with the string that comes off there, because it's just not how it works. All right, so notice this tangent nature of the direction of our force, right? If we again look at, well, relative to point of contact, I've done this carefully such that here's the line of action of that force F. Let's zoom in. Here's a vector R perp to that force, right? And well, this force creates a torque that way, and therefore an alpha counterclockwise. And yes, this thing will maybe do a little more what it feels like that last one would have done, and this thing will ACM to the left, again because it has to translate in the same direction or in an analogous direction to this direction of that rotational angular acceleration. Okay, it's also pretty cool. What's this one? It's also pretty cool if you try it carefully. You can pull in such a way that the spool cannot roll. All right, and look, I got myself hey, look, some students built this some years ago. Breed Dungate et al. And notice this is set up right now in such a way this string over here ends up going up around, and there's a mash, there's a pull, like quite literally, this is what was happening. I should have had a better picture. And the thing is, the wheel is quote unquote, the spool is quote unquote just sitting there. All right. Well, if you look real carefully, if we extend, if I'm careful, extend the line of, ooh, wow, nailed it. Sort of nailed it. I'll fudge it a little bit. There's some, I don't know. But notice where the line of action of this force goes through. It goes right through point of contact. So if we pull in such a direction that, well, there's a frictional force. Guess what? There is a frictional force here. Let's talk about this one a bit. But this so happens, okay, there's a frictional force that acts here, but it acts at the point of contact or at our chosen origin, and thus the torque created by friction is zero. All right, there's this, it's called this tension force. If we orient it just so, such that its line of action goes right through point of contact, then the torque created by this tension force is also zero. And this thing has, well, therefore, if the net torque is zero, the alpha is zero, and then the ACM, or the A tangential of any location, has to be zero. And this thing, quote unquote, just sits there. Right? What's neat to see is, all right, there's a tension force that looks like that. which has an x component that if I, choose an arbitrary scale for how big this tension force is, that's the size of Tx. Well, guess what? That's the size of the friction force, right? And if we actually know, like, how much stuff did I hang over here, we could calculate the, the blah, 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 the tension on that string. And there's a way to find this angle. And then therefore we could actually find this x component and calculate what the friction force is. That's static friction force, which is likely not, it's likely not mu n, because no one says this thing is just about to slip. Yeah. I actually challenge you to do that. I'm letting you read. This Q, I forgot to make it a theta. The answer to this question is, this is the answer. It's a neat little, it's more of a geometric, trigonometric proof. Okay. Okay. Yeah, so the quote unquote this can't roll is the one that, well, you have to have a force that, goes from point of contact through, which I'm making it, yeah, there we go. It would look like that. Yeah. And the Y is, well, the net torque is 0. Right? Or really, it's because the line of action of that force goes through the point of contact, and thus, right? And there's a friction force, like we said. Yeah, I think we've established that there is no torque acting on this object. I mean, what we haven't said is, well, sure, there's this object's weight that acts at center of mass and does this, and and of course that goes through point of contact also. Okay, sure, there's a normal force that goes like this, and well, it's probably now smaller because of that tension force. And that doesn't create any torque. So there's lots of forces. None of them happen to create any torque. Therefore, this thing can't accelerate angularly. Now, what we can do is, in other cases, nice graphic, we can talk about cases in which forces are applied to different forms at different locations and figure out things like, how big is the friction force? What direction does it point? Right? Well, it certainly acts there. We don't even know what direction it points. Well, this sort of screams for, there's an unknown force. It screams for, let's run a net torque analysis, and let's call our origin the place, the point of action of that unknown friction force. So here's a vector r to f. Our net torque statement says f times about r to f times f equals quote unquote I alpha. All right. All right. R to f happens to be, look, it's big R plus 2/3 more of that, so it's 5/3 R. Now, notice. This is a cylinder. Okay, let's stipulate I center of mass of a cylinder is 1/2 mr squared. That's something that many of you are familiar with. And that is this thing's rotational inertia about an axis that passes through its center of mass. But what we are saying is, we are, via our net torque analysis, choosing an axis of rotation, saying, let's say this thing rotates about its point of contact. So what that means is we've got to do a parallel axis theorem, rotational inertia. As a refresher, the way that I write this is I pat is I center of mass. We have to take the fact that the form rotates about its own center of mass, but also the fact that its center of mass actually revolves around the point of contact. So we treat it like a point mass. All right, so yes, this whole thing rotates like that about center of mass, but then the center of mass revolves around our chosen origin. Okay, so this I pat, there's our 1/2 mr squared, and then a point mass is quote unquote m how you see this typically in the text is what you'll see ICM plus quote mh squared, where h is the distance between the center of mass and the chosen axis of rotation. In this case, that is r. So our IPAT is 3/2 oops, come on now. What's happening? Oh boy. MR squared. Okay, so we got 5/3 RF equals 3/2 MR squared alpha. There's some algebra to do, I suppose, if you'd like, but let's do it in a minute. Now what we want to say is, what I'm going to say, or a way to go now is to say, let me shrink, is to relate rotational stuff to translational stuff. And specifically, we're going to do that by saying, aha, there is this alpha that can be related to the center of mass acceleration because, oh, this is what, look, these things are all, like the force is applied to each form which rolls without slipping, rolls without slipping, rolls without slipping. The rolling without slipping criteria are these. That's one. Here's two. Okay, so this alpha is ACM over R. All right, so we can say this 5/3 RF 3/2 MR squared ACM over R. Look what happens. R and then R and then this looks like 10/9 F over M is ACM. 10/9 F over M. ACM is 10/9. ACM is 10/9 F over M. Doesn't look like it, doesn't it? Or does it? And here's what I mean. Here's a big deal. Sometimes you can, or a strategy of mine for figuring out things about friction sometimes says, what if there wasn't friction? Right? Well, this says if there wasn't friction, sort of says if there wasn't friction, this thing ACM's to the right at that rate. Well, if this were the only force, if not for friction, a simple net F would say that, I mean, this without friction says this, right? ACM, ACM. This says that with that as the only force, that's how much ACM you get, but we've got an extra ninth. You dig? An extra ninth. So this tells us, because this thing accelerates faster than simply F over M, aha, there is a friction force acting at point of contact that must point right to account for the more than F over M acceleration. Yeah? So this is our way of saying, aha, friction points right. And well, now watch this, a net F, we can now say, well, these things we have discerned, or we have justified that they point in the same direction, ACM, and then we can say how big is friction force? Well, let's see, we get F plus F is MACM, 10/9 F over M. Yeah. F is 10/9 F minus F, 1/9 of F. Not bad, right? So it so happens that if you have a spool with this geometry, and the spool can be treated like a, well, I guess it wouldn't be a spool because it's got to be a solid cylinder slash disc thing, but somehow we apply a force, at that location. Well, the friction force happens to point to the right. It happens to be precisely 1/9 of the applied force. Let's try another one. Let's say here's a sphere, a solid sphere, right? Where we say ICM of a solid sphere is 2/5 mr squared. So let me take and just shrink all this stuff. Okay, so let's see. We got a sphere here that we happen to somehow apply a force F to the same spot. Let's do the same thing. Let's take our point of contact as origin. There's R to F. Net torque says R to F times F is I pat alpha. This is 5/3 F is, okay, I pat is going to be ICM 2/5 mr squared plus, well, again, distance from here to center of mass is called h, so that's another mr squared. Alpha, well, alpha I'll go ahead and substitute right away for ACM over R. Oops, 5/3 RF. Okay, so let's see. 5/3 RF is 7/5 mr squared ACM over R. All those go. Looks like 25/21 F over M equals ACM. Well, if it's more than ACM, it means, yep, there's a friction force acting that way. You dig? My math right? Yeah. And then, right, a net F says we have figured out that F and friction force point in the same direction. So F plus F is M times 25/21 F over M. And go on and go on. And F is 25/21 minus 21/21, or 4/21 F to the right. Try this one. Yeah. Try this one, a hollow shell. Hollow shell, ICM 2/3 mr squared. Try this one, hollow shell. Again, 2/3 mr squared. Here's the answer. You get a friction force to the left. Try this one. Cylinder. Here's the answer. Good rotational and translational dynamics problems. Okay.